So far, we've considered only the free radical halogenation of ethane, which has cis-identical hydrogens. So the only possible product would be chloroethane. Now let's consider the free radical halogenation of a molecule that has more than one type of hydrogen. And the example I'd like to use is 2-ethylpentane. Because 2-ethylpentane has primary, secondary, and tertiary hydrogens. And if we write all those hydrogens in, we can see that the overall molecule is C7H16. And there are 3 primary carbons, methyl groups, 3 secondary carbons, methylene groups, and 1 tertiary carbon. So of those 16 hydrogens, there are 9 primary hydrogens, 6 secondary hydrogens, and just 1 tertiary hydrogen. If we subject 2-ethylpentane to free radical halogenation, with fluorine and bromine, in each case, we should get 3 possible products. Bromine, the same 3 possible products. There are 3 possible positions that the halogen can be introduced. So we would have, for example, 1 fluoro, 3 ethylpentane, 2 fluoro, 3 ethylpentane, and 3 fluoro, 3 ethylpentane. And the corresponding 1 chloro 3-ethylpentane, 2 chloro 3-ethylpentane, and 3 chloro 3-ethylpentane. And the same for the bromo. I'm sorry, it's 3-ethylpentane, not 2-ethylpentane. Set up. If we measure the percentages of each of those materials that's isolated, we will find that for the fluoro case, we get 51.2% of the 1 fluoro derivative, 40.9% of the 2 fluoro derivative, and 7.9% of the 3 fluoro derivative. For chlorine, those percentages are 23.7% and 13.1% respectively. And for the bromine, 0.4% of the 1 bromo 3-ethylpentane, 21.9% of the 2 bromo 3-ethylpentane, and 77.7% of the 3 bromo 3-ethylpentane. So you notice that the major product is different for each of the halogens in this particular system. The major product for the fluorine is the primary chloride. The major product for the chlorine is the secondary chloride. And the major product for the bromine is the tertiary bromide. For both the chlorination and the bromination, we've got a good enough yield of our major product compared to our minor products that it might be synthetically useful, particularly for the bromine. For fluorine, we get a complicated mixture that's going to be difficult to separate. So we need to ask ourselves two main questions. Why is the selectivity different for the different products? And why is the major product different in all three cases? Statistically, if every time a halogen radical collided with a hydrogen, it reacted to form the hydrogen halide, we would expect to get a ratio of 9/16 to 6/16 to 1/16. And so statistically, if every collision was effective, we would expect to see 56.25% of the primary halide, the 1-fluoro-chloro-bromo 3-ethylpentane. We'd expect to see 37.5% of the secondary product, and we'd expect to see 6.25%, reflecting the fact that it's 9 times as likely to collide with the primary hydrogen as with the tertiary hydrogen, and it's 6 times as likely to collide with the secondary hydrogen than the tertiary hydrogen. We know from collision theory that the rate constant, the rate of a reaction, the rate constant, depends on 3 factors. And we know that K, the rate constant, is equal to Z times P times F, where Z is the number of collisions, which depends on the number of each type of hydrogen. P is the proportion that have the proper orientation. With the orientation factor, that's not really an important factor in free radical halogenation because the radical, the halogen radical that's attacking the hydrogen is a sphere, roughly. Right? So it doesn't really matter how it contacts the hydrogen. And F is the fraction with enough energy to exceed the activation energy barrier. And we know that that is equal to e to the minus EA over RT. And then the Arrhenius equation comes out of this, where we group the proportion with the proper orientation with the number of collisions to call it the pre-exponential factor A, and A is equal to A e to the minus EA over RT, the familiar Arrhenius equation. So we know that statistically, if every collision had enough energy, the number of collisions would be reflected in the percentage distribution. And we would have 56.25% to 37.5% to 6.25%. Fluorine comes relatively close, 51.2%, a little less than 56.25, 40.9, a little bit more than 37.5, and 7.9, a little bit more than the 6.25. But the other two don't come anywhere close to the statistical distribution, which suggests that there's a difference in the fraction that have enough energy to overcome the activation energy barrier for colliding with the secondary hydrogen than there is for colliding with the primary hydrogen or colliding with the tertiary hydrogen. So there must be a different reactivity. The relative reactivity of the primary, secondary, and tertiary hydrogens must not be the same. And the relative reactivity must be different for bromine than it is for chlorine, and different still for fluorine. So what we'd like to do is we'd like to come up with the relative likelihood of a particular hydrogen actually reacting with the halogen radical to form the hydrogen halide and the carbon radical. And that number which corrects for the proper orientation, is called the relative reactivity. And what we know is that the observed percent is going to depend both on the statistical factor how many hydrogens of each type there are, right? The number of collisions, and the relative reactivity of that hydrogen. How likely it is that that collision with that type of hydrogen is going to have enough activation energy, to exceed the activation energy barrier. So this is the Z in the collision theory, the Z times P times F, and this is the F, right? So we got Z times P times F, where F is equal to e to the minus EA over T. P is not a factor because we're working with a spherical halogen radical, and Z is the number of collisions. So we can correct for Z by dividing each of those percentages through by the number of hydrogens of that type. So there are 9 primary hydrogens. We can divide 51.2% by the 9 primary hydrogens. There are 6 secondary hydrogens, so we will divide 40.9% by the 6 secondary hydrogens. And there's only 1 tertiary hydrogen. So we'll divide that through, and we'll end up with 7.9 here. 51.2 divided by 9 is equal to 5.69, and 40.9 divided by 6 is equal to 6.82. So the ratio of reactivity should be 5.69 to 6.8 to 7.9 for a primary hydrogen versus a secondary hydrogen versus a tertiary hydrogen. So what we're doing is we're calculating relative reactivity by rearranging this equation. Relative reactivity is equal to observed percent divided by a statistical factor. And for fluorination, we should get a ratio of 5.69 for the primary to 6.82 for the secondary to 7.9 for the tertiary. We'd like to normalize that so we get a number that's 1 for the primary by dividing through by 5.69. And we come up with 1.2. So a collision of fluorine radical with a secondary hydrogen to form 2-fluoro-3-ethylpentane is 1.2 times as likely to happen as the collision with the primary hydrogen to form 1-fluoro-3-ethylpentane. And the tertiary hydrogen is 1.4 times as likely to have enough energy to get over this activation energy barrier as the primary. Not very different from 1 to 1 to 1, but a little bit, right? So the tertiary product is there in slightly larger quantity than we would predict based on statistics. The secondary one there in slightly larger amount than we would predict based on statistics, and the primary one is there in a little bit less than we would predict. We can do exactly the same analysis for the chlorine, divide through by the 9 primary hydrogens, divide through by the 6 secondary hydrogens. There's only 1 tertiary hydrogen, so we won't actually have to do anything here, but it'll stay 13.1. And we can do the same for bromine. 0.7 divided by 9 is equal to 2.63. And 63.2 divided by 6 is equal to 10.53. So we think that our ratio here will be 2.63, 10.53 to 13.1. And we want to divide those each by 2.63, so we normalize this to defining the primary as 1. And we get 4. And we get 5. So for chlorine, the chlorine radical is 4 times as likely to react when it hits a secondary hydrogen as when it hits a primary hydrogen, and the tertiary hydrogen is 5 times as likely to react when the chlorine radical hits it as the primary hydrogen. With 4 divided by 9 is 0.044, and 1.9 divided by 6 is 3.65. So our ratio should be 0.044 to 3.65 to 77.7. And if you divide through by 0.044 to normalize 1 as the primary reactivity, 3.65 divided by 0.044 is equal to 83. And 77.7 divided by 0.044 is equal to 1766. So what we predict is that bromine radical is a lot more selective. It's more than 1,700 times as likely to react when it hits a tertiary hydrogen as when it hits a primary hydrogen. And it's on the order of 80 times as likely to react when it hits a secondary hydrogen as when it hits a tertiary hydrogen. In fact, if you look in your textbook, the numbers given for bromine are 1 to 80 to 1,700. Because in your textbook, it's based on a large number of different primary hydrogens, secondary hydrogens, and tertiary hydrogens from a number of different molecules. So 1 to 1.2 to 1.4 is not particularly selective. Chlorination is exothermic. The reaction goes. It's usually not even controllable, and it won't be selective anyway. Chlorination is selective, but nowhere near as selective as bromination. In all cases, the tertiary hydrogen has the largest relative reactivity, followed by the secondary hydrogen, followed by the primary hydrogen. So we now need to answer 2 questions. Why is it that the tertiary hydrogen is always more reactive than the second, and the secondary is always more reactive than the primary? And if we put methyl on there, the primary is always more reactive than methyl. And we need to answer the question, why is bromine so much more selective than chlorine, which is in turn more selective than fluorine? So we've got a difference in selectivity, a difference in relative reactivity for fluorine and chlorine and bromine, and the tertiary hydrogen is always more reactive. Those are 2 different questions that we need to address in the next 2 videos, and we will do that by using the kinetics of the reaction.